The main experiment that we do when we talk about interference is this one. We have two little slits, and we pass some light through, and we get a pattern on the back screen. What is this experiment called? It's in the video. It's named after a guy.
Yeah, a lot of guys.
Young's double slit experiment. One of the most famous experiments in all of physics. Okay, so we end up with this pattern on the back wall where we have waves interfering constructively and destructively. So that's what this kind of slope thing is kind of representing. You have places where waves from the top little slit interfere and waves from the bottom slit interfere. And they can combine in two ways. They can interfere together so that they give a bright spot, so that they give a big peak, or that they can combine so that they cancel each other out. That's a dark spot. And we label all of these spots as something called an order. We use m equals 0 for the middle order, then m equals 1, and m equals -1 for the first order, both above and below, and m equals 2, m equals 3, 4, so on and so forth. We also do this for the dark spots. The dark spots, you would have the 0th dark spot would be actually 2 of them on either side. Okay? And then m equals -1, -2, 1 and -1 for the dark spots where things are canceling out. We use different kind of things that we're measuring inside of this Young's double slit. We have the slit separation. This is labeled with a lowercase d. We have the distance from the slits to the screen. That's labeled with the big D, large capital letter D. And then we also have the distance from their bright spot, from the middle, kind of central bright spot, to where your next bright spot forms. We call that Y. So this would be Y sub 1 because it's the first order bright spot. We can go up to the second order bright spot. That would be Y sub 2 and so on and so forth. And we use all of these equations. We can figure out some math, do some trigonometry to figure out what all these equations are. The Y value, the height that you are above that middle line for any given order, if you algebraically and geometrically figure this out, your book shows you the calculations. It's equal to m, which is the order number, times lambda, the wavelength of light that you're shining through these two little slits over here on the left, times capital letter D, which is the distance from the slits to the screen where you're forming your image, all divided by lowercase d, which is the size of the slits that you're passing the laser through. And you can use geometry to prove all of that. Right? Yeah, you all know how to do that, right? Piece of cake, easy peasy. We don't need to bother doing that on an exam or anything like that. Any old baby can do this. If you want to get an idea of what this actually looks like, you can also look at figure 3.5b in the book. That kind of helps give you a visual. Other equations we want to know for Young's double slit. We want to know the equations for getting constructive interference, so waves combining. That's going to be m, which is your order, times your wavelength, equals d times sine of theta. Sine of theta. For our purposes, we're just going to approximate it. This isn't technically correct, so I probably shouldn't post this on YouTube because a bunch of physicists will come and yell at me. But we're going to ignore that for now. And we're going to, this is roughly equal to the angle theta. Okay, so we are drawing a right triangle. This is a right triangle from the center to the first order bright spot. And we are drawing a triangle out of that. Right triangle. And that angle is theta. So m times lambda equals d times sine of theta to give you constructive interference. So waves combining together. And this is where m is equal to 0, 1, plus or minus 2, so on and so forth for all the orders. If I want the waves to cancel each other out, I get destructive interference. Again, this is all just a review of all the stuff that's already in the lecture video. We have m plus 1/2 times the wavelength equals d sine theta. The order is, again, 0, plus or minus 1, plus or minus 2, so on and so forth. These are the primary equations that we need to know, that we need to use. In fact, I'm going to have you use this equation for an in-class assignment, so make sure you know this one. In fact, it's so important, I'm going to write it down up here. M times lambda times capital letter D over lowercase. We're going to use that in an experiment for you. Okay, any questions on this? This is all the basic physics. This is all the basic equations. We all know this, right? Known this for years. Now let's do a sample problem. Let's do part of a sample problem. Problem number 35 is the in-class problem. And in problem 35, we have 10 narrow slits that are equally spaced 0.25 millimeters apart and illuminated with yellow light of wavelength 580 nanometers. It turns out that multiple slit interference uses the same equations as the double slit interference. You can think of multiple slits as just being the double slits multiple times. So same physics happens. So I can use all the same equations. Part A, they want to know what are the angular positions of the third and fourth principal maxima. So let's write down everything that's relevant. 10 narrow slits are equally spaced 0.25 millimeters apart. The spacing of your slits then is D. Lowercase d is the spacing. That's equal to 0.25 millimeters. Biggest place that people make mistakes in these problems is to not convert units to all be the same. I suggest converting everything into SI units, so that would be 0.25 times 10 to the negative 3 millimeters. Then they have, it's illuminated with yellow light of wavelength 580 nanometers. So that's lambda equals 580 nanometers. How do I make that into meters? What is nano? Negative 9. 580 times 10 to the negative 9 meters. What are the angular positions of the third and fourth principal maxima? So part A, they want to know what is angular position. What variable would that be? What variable is angle? Theta. So that's what we're looking for. And they want to know for the third and fourth principal maxima. What is that? What variable is maximum for interference? Somebody said something. The order. And what variable represents order? M. So I need to do this for m equals 3. So I need to find theta 3. And I need to do this for m equals 4. Okay, I have all these variables. I have lowercase d. I have lambda. Theta I'm looking for. I have m. Is there an equation that relates all this? I'm looking for maxima. What's the equation that I use for maxima? Do you remember it?
M over lambda, m times lambda equals d sine over theta, and you can rearrange it.
M lambda equals d sine theta. Okay, let's look at what I know. Do I know what m is? Yep. Do I know lambda? Yep. Do I know lowercase d? Yep. Do I know sine theta? Well, that's what I'm looking for. Right? So this is all good. The one variable I'm looking for is the one variable I don't know. So I need to solve this equation for theta. I solve this for theta by dividing both sides by lowercase d. So m times lambda divided by d equals sine of theta. And how do I get theta by itself there? take the inverse sine of both sides. So if I do inverse sine of m times lambda over lowercase d equals the inverse sine of sine of theta. The inverse sine, I'm doing an extra step in there. You usually don't see this, but inverse sine of the sine is just the angle. So this is theta going to be equal to inverse sine of m times lambda divided by lowercase d. So now I can very quickly solve this. Theta sub 3 is the inverse sine of m, which is 3. Lambda, what's the wavelength of light that I'm using in this one?
Yellow.
Yellow, which is 580 times 10 to the negative 9 meters. And I divide that by the slit separation, and they told us in the problem this was 0.25 millimeters. So 0.25 times 10 to the minus 3 meters. Plug all these numbers in, and you'll find a theta. Go ahead and plug them in. Pop out your calculators. Let's see if I can do it. Put it in your calculator. How many of you got this? Anybody got 0.007? I see some yeses. I see some no's. Oh no. Did anybody get this? If you got 0.007, your calculator is in radians, so switch to degrees. If you are not in degrees, you will get all wrong answers, and then you won't pass the class, and then you won't get your degree. So get into degree mode. You all want to get your degrees, so get into degrees. So we should get theta equals 0.4. If you don't know how to switch into degree mode, just call me over when I start letting you work on your own in your groups, and I will happily come over and help. We need to do the same thing for theta 4. Theta 4 is equal to inverse sine. Now instead of 3, I plug in 4, and then everything else stays the same. 580 times 10 to the negative 9 meters, all divided by 0.25 times 10 to the negative 3 meters. Theta 4. Plug and chug your numbers in. And I got 0.53. What? So make sure you're getting those numbers, and we'll be nice and happy. The part for you to figure out. There's going to be 2 things for you to do in class today. You're going to figure out how to do part B of this problem. Part B is, what is the separation of these maxima on a screen that is 2 meters away from the slits? So let me draw what that looks like. So here's my 2 little slits. There's my screen. We now assume that the distance, capital letter D, is equal to 2.0 meters. You still have the separation of the slits That lowercase d is 0.25 millimeters. You're still using yellow light coming in here. So lambda is still, I think it was 580 nanometers. And you're still going to form this interference pattern on the back of the screen. So you're going to have a central bright spot, and then a first order, second order, third order, fourth order, and you'll have that on both sides. First order, second order, third order, fourth order. And what they want you to find is the separation of these two maxima for m equals 3 and 4. So this is 0, 1, 2, 3, and 4. You need to find the height y4, and you need to find the height y3, and that will let you figure out what the difference is in those two heights. y4 minus y3. And what equation can I use to calculate the y? That one right there. Okay? This should not be super difficult. Now, the other thing I want you to do, I want you to use these setups that you have in front of you. So in front of you, I'll give you about maybe 15 minutes to solve this problem, because to do the next part, we need to turn lights out, because we're going to turn on lasers, and you're going to see lasers shooting all around the room. And what you're going to do is you're going to come and you're going to set up your little tray. Front table is lucky. This is already set up for them. You have a laser, and on your table you should have something that says single slit set. And what you're going to do is you're going to find a single slit. There's a little section on there labeled single slits, and you're going to shine light through one of those slits. Shine your laser through. And when you do that, you're going to see an interference pattern on the screen. Let's see if I can make it work. So I need to turn the lights off really quickly. It's getting dark. So at the front, we can see this, yes?
Yeah.
How about second table? Can we see this? Third table, can you see the interference pattern? You can see this in your book, too. You see there's a big bright spot in the middle, and then there's a dark spot, and then two bright spots on either side, and then two more bright spots. You might need to get closer, and I'll come around and help you so that you can see that. So what I want you to do is I want you to figure out what things you can control about this experiment, so that if I were to come by with a different laser, if I come by with a green laser and shine a green laser through your little apparatus, or if I come by with a blue laser and shine a blue laser, I want you to be able to calculate what the wavelength of these lights are based on stuff that you could control in this little system setup. Okay? So when you're thinking about how to do that, I want you to think about that equation on the board. I want to know how to calculate wavelengths. Okay? That's what I got for you for today. So about 10 minutes to solve your problem, and then start playing with lasers. Here's your laser back.
Yay! Mommy! Well,